Welcome to this very final video on group equivariant graph neural networks, where I want to wrap things up with, the most general class, I would say, of equivariant graph neural networks called gauge equivariant graph neural networks. The idea is that so far we've made this journey from plain neural networks all the way to group equivariant neural networks, both in the regular and the steerable case, where we argued that group convolutional neural networks are really just plain neural networks, but constrained to be equivariant. And this is explained in detail in lecture 1.7, group convolutions are all you need. But the whole analysis so far has been focusing on homogeneous spaces, mostly where we talk about feature maps on spaces on which the group of interest acts transitively. And this actually implies a global parameterization of the group. And this is something that you do not have in the general case of manifolds. So the idea is here we talk about groups acting on spaces where actually as a base space we often consider R2 or R3, so the Euclidean case. And in this case we're going to look at equivariance for spaces that locally look Euclidean but are not so globally. So we enter the regime of manifolds. Okay, so far we covered in lecture 1 the regular group convolution framework, both for discrete groups as well as continuous groups. So the regular group convolution framework was really like template matching with kernels that are transformed under all transformations in the group. Then this approach relied on the idea of extending the domain with an extra access that encodes for all these possible transformations in subgroups. And this is sometimes inconvenient because you need to memorize for all these transformations what the response was. And then we introduced this idea of steerable group convolutional neural networks, where based on a type of Fourier transform, we could get rid of this gridding and work with fields of Fourier coefficients. So this led to this idea of steerable group convolutional neural networks. So here we could get rid of this gridding altogether. And as a reference, we relied on this terminology and this whole idea of steerable feature fields. And we also discussed how to work with feature fields and how this is coded up in this ESCNN library for steerable convolutional neural networks. Then even though this library codes things up for 2D and 3D altogether, in lecture 3 we were focusing mostly on the 3D case and on point clouds, where this library and the method so far were focusing on dense feature maps like 2D images or 3D volumes. In lecture 3 we covered this idea of equivariance for point clouds in 3D, and then it becomes a bit more intuitive to analyze things locally in terms of message functions. And we showed that we can construct equivariant message functions also in the steerable setting based on the Clebsch-Gordon tensor product and irreducible representation theory for the SO3 or O3 group. And the code that implements all this theory is nicely presented in this E3NN library, which you can get a bit of experience with our tutorials. But central, both in lecture 2 and 3, is the idea that we implement mappings between steerable feature fields, where the fibers transform under representations of a subgroup. And in both cases, the base domain was just the 2D plane or the 3D space or plane, like R2 and R3. Now, to make things a bit more general even, the gauge equivariant framework shows that we can extend these group equivariant methods to arbitrary manifolds that locally look like RD. But this requires the introduction of a notion of gauge frames, which I'm going to do in the remaining part of this video. Okay, a quick recap of feature fields and induced representations, mainly the feature fields aspect. So this was presented as a feature map that maps a point in a Euclidean space, so a base point, to a steerable feature vector. And such a feature vector was steered or transformed via a representation of a subgroup H. So I have a whole field of fibers that transforms via some representation of a group H. And then these feature fields, they transform via the transformation acting on the domain of these fields and the codomain. And by this we can code up scalar fields, just like we've been using with conventional CNNs or group convolutional neural networks. But we could also build a steerable group convolutional neural networks with this by assigning steerable vectors to each base points. Yeah, and this is a very general way of representing data. So with steerable feature fields, the idea is that, well, in the regular group convolution case, so lecture 1, we extended the domain by sampling all these transformations of the kernels along an extra axis. And if you look at it locally at a fixed point x, what you do is actually storing a fiber of responses for all different rotations. And we show that such fibers transform by an action of SO2 in this example by just a periodic shift along this axis. So we have a regular representation acting on these fibers. And via Fourier transform, we can turn these fibers into vectors of Fourier coefficients, which transform via the irreducible representations of the group. So by treating such G feature maps as steerable feature fields, we gain a bit more of theoretical and mathematical flexibility, but also coding flexibility to choose whatever representation we want. Sometimes it's convenient to work with regular representations, for example, if you want to apply pointwise activation functions, and sometimes it's more convenient to work with steerable, with irreducible representations, because that reduces the computations to these block diagonal multiplications. Okay, so we've covered how to work in all these 3 settings. Now the essence here is that the domain of this space is R2. So to each point in R2 I can assign a fiber, and this fiber has a particular meaning. So this is color coded. For example, red means to the zeroth orientation, for example along the x-axis. And this notion of red, so what does orientation mean? So it all points in this direction, stays the same over my entire manifold. So I have a global parameterization of a reference frame. So everywhere I look, red means the same, pointing in this direction. But in general, on manifolds, you do not have this. If you have a torqued or curved manifold, then you cannot use one and the same frame everywhere in your space. And that's going to be explained next. Now, when we want to apply the same principles to manifolds or feature maps on manifolds, such as this torus, for example, we have to introduce a notion of gauge frames. And that's very neatly explained in this comprehensive paper or book, Coordinate Independent Convolutional Neural Networks. So I'm going to use this paper as a reference. So this is the paper with main author Maurice Weiler, whose name we've seen pop up several times already. Yeah, let me go straight to the motivation of working with local reference frame and this global parameterization, which you cannot always have on all types of manifolds. So the idea is as follows. So when we talked about convolutions and group convolutions, we often talk about weight sharing, right? That we want to detect the same pattern everywhere in space in the same way. So we have weight sharing over, let's say, trajectories. So we have this filter, we can move it to this other point in space and just check for the presence of the same pattern at that location. And the way how I move this filter about on my Euclidean plane doesn't matter. So if I take this path, it still looks the same whether or not I take this path. But suppose I want to do now the same on the sphere, which locally looks like a 2D Euclidean plane, right? So if this filter, I want to detect the same pattern here at the north pole of this circle. So I just move it there and check for this particular pattern. Yeah, I can do that, but this definitely is path dependent, this moving of this filter, because rotations do not commute and the sphere is a homogeneous space of rotation. So if I move this filter now, let's first check what the filter looks like at this point on the sphere and then move it in this direction. So I end up with the same location, but you see now my filter is rotated. This red part is pointing in that direction, and here the red part is pointing in that direction. So the way I'm doing my weight sharing on manifolds in general is path dependent. So here we have this rotational aspect to it. And another example is this manifold, this torus, the Möbius strip. If I move along this surface, that at some point I'm looking at the bottom of this filter, right? It twists around. And if I then move again, it changes its orientation again. So here, if I locally move this filter forward, its orientation stays the same. But now if I move it all the way back over the surface, you see its orientation flips. Now the red part is pointing in this direction as opposed to this direction, this versus this. So we have a flipping of the kernel going on. So apparently the way I'm going to define weight sharing depends on the path. If I take one turn or two turns, it really depends on what kind of pattern I'm looking at. Okay, and now we want to get rid of this ambiguity. And the way we can get rid of this ambiguity to always say relative to which frame is this filter defined. And so that's explained over here. So in principle, I can describe my feature vectors relative to a certain frame at each location, and then just move my filter to each frame point. But of course, I'm free to define the frame however I want. I could always say, okay, maybe this is my reference main axis and this one, and I can scale it. And then the filter looks relative to this frame different everywhere I look in space. But I'm allowed to do this to define features in terms of these reference frames. Now, the idea is that if we talk about weight sharing via symmetries, as we did by the group convolutional framework, this works as long as we work with a transitive action. If I work with homogeneous spaces. So if I am able to move my filter everywhere in space because I have a global parameterization, let's say this works. Then we just saw in this figure that, okay, well, maybe we can change our viewpoint and talk about weight sharing over trajectories. And again, this works in the Euclidean setting, but not on manifolds in general, where we have this path dependency there. So, well, that's explained as the limitation over here, where the limitation is that different paths lead to different kernel alignments. So what they then do is they introduce this notion of kernel alignment based on weight sharing along frames. And this then allows to formalize this notion of kernel alignment, where in a way, all these filter responses are the same relative to these frames. So I use the same convolution kernel, but the frame changes. So we have still weight sharing going on, but at each point in space, I'm going to change how I'm going to look at the data. And then the idea is, of course, that maybe we want to be locally rotation equivariant. So we want to detect this pattern for all possible rotations, which you can think of it as looking at this filter under all possible frames at this location. Well, this is of course computationally prohibitive, but via steerable methods, we can use this as a reference frame and work with steerable convolution kernels to encode for all rotational responses locally. Okay, so the challenge is of course how to be able to work with all possible frames at each location. And that then motivates the need to talk about G structures. And this will be the roadmap towards steerable group convolution methods on manifolds. So the idea is that each location, we have a lot of possible frames. So we have an entire space of frames denoted in a particular way, FPM. And the idea is that generally you want to work with a particular metric structure, so how to measure vectors in these tangent spaces, and you want to typically do that via an orthonormal basis. So that's explained over here. But the idea is, of course, that we want to maybe assign only one frame at each location relative to which we're going to describe a filter. I can describe this filter relative to this frame. I could rotate the frame and could still describe the same filter, right? We saw that also via change of basis in one of the previous lecture. So the choice for which frame I'm going to place at each location is a bit arbitrary, but the entire set of frames that I can assign there isn't arbitrary. So what we're going to do, or what's being done in this paper then, is introduce the notion of a G structure, saying that one frame can relate to any other frame via such a change of basis or via a transformation that maps one frame to the other. So it says G structures are bundles of distinguished reference frames on M. So bundles of reference frames, at each location I have a reference frame. A bundle of reference frames such that the gauge transformations between frames of the same tangent space take values in the structure group. So this G is called the structure group, the group of transformations that allows me to locally transform one frame into another frame. Okay, so the idea behind gauge equivariant CNNs is that we're going to build feature maps by describing the feature vectors relative to a basis assigned to each point in space. And in principle, this basis or this frame is arbitrary, right? A vector, it shouldn't depend on the basis in which it is represented. And in that sense, neural networks on Riemannian manifolds with a G structure should be based on GM coordinate independent operations, where this coordinate independence means that all geometric quantities, so the feature vectors and functions between them, should be equally well expressible in any gauge. Okay, and then this figure is given, right? So these are several choices of gauge frames. So in this case, suppose we do only translational template matching with a filter that is, for example, horizontally aligned. And I only want to detect this pattern under a particular orientation. Then this is the reference frame, and I'm not interested in transforming locally this frame to any other rotation or orientation. So the structure group is just the identity. I only consider these frames. But suppose now I want to detect this feature under all possible orientations, then I should be able to describe this filter under also this change of basis, where now the structure group is the whole group SO2, meaning like I do not want to make a choice on a particular horizon direction, let's say. I want to be able to consider all possible rotations. So the structure group is the group of all rotations that can map one frame to the other. And this becomes especially important when you talk about the sphere, where we cannot pick one main orientation, because then at the North Pole we have this singularity going on over there. So basically we're saying here, at each point on the sphere, we have this planar tangent plane, so a tangent, a gauge frame. And since my chosen gauge frame is arbitrary, I want to consider all possible directions locally. So I have again a structure group SO2 attached to each point in my tangent space. And of course, when you talk about spheres, we can extend it a step further and talk about manifolds or shapes in general, which all look locally Euclidean. Okay, and then also in this case of this Möbius strip, where we have this reflectional ambiguity going on, we can get rid of this ambiguity to always consider two frames. So either I'm going to describe my pattern relative to a frame which is oriented in this direction, or relative to this frame. And I can transition between one or another via a reflection. Okay, and this then brings us to the steerability aspect, that we want to be independent of the chosen frame. So we should be able to transition from a descriptor relative to this frame to one relative to that frame. So that brings us to a notion of steerability that is then described in this section. If I want to have this coordinate independent, so frame independent, let's say, and I want to have weight sharing, then I need G steerability. It means that my kernel, the convolution kernel, should be steerable via transformations in this structure group. For example, if I have a convolution kernel which is reflection steerable, so I can flip this kernel just by multiplying with -1, then blue becomes red and red becomes blue, then I can also have this steerability in here. Suppose I have a gauge frame where the structure group is this flip symmetry, right? So I either consider frames in this direction, but I also, for example, have to deal with this ambiguity that I also want to consider this flip direction. So I can turn this frame into this frame via an action in the G structure group, so reflection. And then I can do template matching either in this frame, so I align the kernel with this frame everywhere in space, and it gives me these results. And if I want to know what the result would have looked like if I convolve this with the flipped kernel, then I just apply the steerability condition on the feature maps, just like we saw in the steerable neural networks. I obtain the result from this to this via an action of the representation on these fibers. So I turn this response blue over here into red over here. So if I have steerable kernels, then I only need to consider one set of gauge frames from which I can obtain the results for the other directions. And linking this back to what we've seen before, suppose we want to have SO2 equivariance locally, then we can convolve with a rotation steerable filters, for example, all with the same, relative to the same reference frame. And then I can also recover what the result would have looked like if I were to convolve it in this direction or this direction, simply by letting the representation of SO2 act on the fibers, which are all specified relative to this original gauge frame or gauge direction. Okay, so that's what I want to say about this paper. The idea is that we assign to every point in space a gauge frame, And if we have ambiguity, for example, if we also want to consider all possible gauge frames, then instead of testing or let's say doing convolutions relative to all possible gauge frames, we only do it, we select one gauge frame at each point and make sure that we work with steerable convolution filters such that we can always transition to different frames afterwards via representations of the G structure group. So this whole steerable framework falls within this category of gauge equivariant CNNs, but the gauge equivariant CNNs have the advantage that they generalize to other types of manifolds, such as, well, the sphere is a homogeneous space, but if we consider non-homogeneous spaces, such as these shapes, which locally look Euclidean, or these Möbius strips, which also locally look Euclidean, then we can still build equivariant architectures for these types of data. Alright, so that's explained in great detail in this paper, Coordinate Independent Convolutional Neural Networks, which I think you are now very well prepared to reading. And I think this is a masterpiece that covers, let's say, the entire field so far. I'll get back to that point in a couple of minutes. Okay, now let's go to a specific instance of a gauge equivariant CNN, in this case specific for the icosahedron. So this turns out to be a very efficient alternative to all these spherical CNNs out there. And this is really the paper that kicked off this line of research in gauge equivariance. Okay, I'll try to stay on a high level here, not going into too much detail, but this is what we've covered so far. If we have a sphere or like a manifold in general, then we cannot always find a global parameterization or reference frame. For example, we can use this red grid of references, but at some point we reach a singularity and where all these direction vectors start to spiral around each other, and there's ambiguity in what is now my main directions. And so we can get rid of these singular points by working with multiple charts. So I can use, for example, this red reference frame relative to which I can describe a feature, or I can use the blue reference frame relative to which I can write the same feature or detect the same feature. That's actually illustrated over here, right? So if this green arrow, I can describe it relative to this red frame, so then it's pointing upwards, let's say, or I can describe it relative to this blue frame, and then it's pointing a bit more in the horizontal direction. And by working with multiple charts, we can get rid of these singular points. So sometimes we describe things relative to this frame, sometimes we can describe things or want to describe things relative to that frame. Alright, so this shows that we can work with different reference frames or gauge fields of gauge frames, but there's still this ambiguity in like the orientation. Now, if I want to have a convolution filter, for example, I want to apply it to this direction and this direction and this direction, but then how specifically I want to describe this filter, whether it's relative to the blue or the red frames, that's somewhat arbitrary. And so that's what they are going to do in this paper. So essentially they're going to do group convolutions, either relative to the blue frame or to the red frame. And at some point they need to transition between the two. And that happens via these gauge transformations. Okay, so that's what they described then here in this paper. So again, talking about feature fields, right? Where these feature vectors are relative to a reference frame. And these feature fields, they are transformed via representations of the group. And it turns out if you pick the feature fields to transform under representation of the structure group, so the same group that consists of the transformation that I allow for switching between gauge frames, then I'm able to extend this idea of steerable group convolutions to this manifold setting, simply by working with change of basis every now and then. Okay, so here they work with steerable feature fields of a type rho, right, where the codomain transforms via representation rho. And in this particular case on the icosahedron, they figured out that they can use this nice hexagonal structure or gridding of the space and work with regular representations. And now the idea is that in every point in space, the feature vector is defined relative to a reference frame. So if I want to evaluate the result of the convolution filter at a certain output location P, then I'm going to integrate over its entire neighborhood, right, with some convolution kernel. But that means I need to aggregate feature values coming from different tangent spaces or different that are defined relative to different frames. So I first need to put all my neighbors which are steerable vectors relative to their corresponding frames. I need to put them in a common frame, namely the reference gauge frame at location P, via a change of basis, which is encoded via this representation or this transformation acting on the fibers of the neighbors. So this is really just a steerable group convolution, but in the steerable setting before, we didn't have this component here, because everywhere we were able to use the same reference frame. But now we work with gauge frames, and then we need to encode for every point pair this transitioning from the frame in which the neighbor is defined to the frame in which the point P is defined via this particular representation acting on these fibers. Okay, and that's it really. And now the nice thing is that we do not necessarily need to handle these transformations for every possible point pair. If we talk, for example, about the icosahedral grid or the icosahedron, we can come up with a particular gridding that splits the icosahedron into domains on which I can use one and the same frame. And then on this location, I have to switch to a different reference frame. But then this allows us to sort of unfold this icosahedron in these pieces, glue them together, and only at the cases where I switch from one frame to the other, I have to take this transitioning of reference frame into account. And I think that's what they brilliantly did in this paper. So by unwrapping this icosahedron, they essentially end up with a global 2D plane, but occasionally they have to take this transitioning into account via pre-computed transformation matrices. And that allowed them to implement this simply via conv2D operator instead of explicitly, for example, by a graph neural network encode for every possible neighbor pair interaction. So that's explained over here. This is this padding to take these transitions into account. They talk about the icosahedral grid to not only encode for, let's say, 90-degree rotations or, so by working with the icosahedron grid, they work with 6 rotation angles without having to rely on the steerable representation theory. And that allowed for very efficient implementations. And I think the rest is just showing that it works really fast and really well. Okay, so that's really the first instance of this gauge equivariant CNNs. And then I also want to point towards this paper where also the spaces, so this is on mesh CNN, so on meshes in general, which locally look like 2D planes. But in this case, we do not have these nice big regions which we can unfold into a flat plane and then use the conv2D operator. This really has to be implemented in a type of message passing framework. But the idea here is, of course, essentially the same. At each point, we can define this 2D plane and a reference orientation, for example, one of the edges in this mesh, and we can do that for every point in space. And if we want to then propagate information at one location to the other location, we first have to apply a change of basis. And in this case, in contrast to the previous paper, which was based on this regular representation, here they work with steerable features, as to be able to handle all possible rotations between reference frames. Okay, so I really encourage you to take a look at this paper as well. But I want to point out that this paper covers all the theory, but also goes into great detail in all the methods that fall within this framework of gauge equivariant CNNs. And that basically is everything that is equivariant in some sense. So both the regular group convolutions, the steerable group convolutions, but also several graph neural networks that are, let's say, locally equivariant. And with respect to that, I think this is definitely worth also a mention. This is maybe one of the first, or maybe the first instance of a gauge equivariant CNN called Geodesic Convolutional Neural Networks on Riemannian Manifolds by Jonathan Meske and Davide Boscaini. And it's nice to read this paper in light of this gauge equivariant framework, where in this paper they also construct local gauge frames on meshes and then detect features relative to these main orientations, but then rotate these convolution kernels over a subset of rotations and then pool afterwards. So they do not stick to this general group convolution framework, but instead obtain locally invariant features by matching against filters which are anisotropic, but which are tested under all possible rotations locally and then pooled afterwards. All right, so that was quite a journey, right? We went all the way from plain neural networks all the way to gauge equivariant CNNs. So I think we've covered now everything about equivariant neural network, which is currently out there in literature. And so we followed indeed this trajectory more or less in a historical sense, going from plain neural networks to CNNs to regular group convolutions to steerable ones, steerable in 3D to gauge equivariance. And this whole trajectory follows actually to a large extent the work by Taco Cohen, right? So in his PhD thesis, he also goes over this structure, and you see Taco's name pop up in all of these seminal papers out there. And I think it's a great read if you want to go into details about all these different methods. Where he ends his thesis with this part on gauge equivariant CNNs. But I also want to mention, of course, that if your objective is to really understand this general framework, then I also recommend reading this paper, because this has this scope and general viewpoint in mind from the start. And it also nicely builds up with a lot of nice visual examples. Okay, with that I would like to conclude. I hope I've provided you with enough background information and enough detail to understand the regular and the steerable group convolutional setting, but also have an idea of what's happening in this gauge equivariant framework. And I really hope that at the very least you now understand the core concepts and mathematical tools such that you can start reading those papers, implementing those papers, like play around with them, build your own equivariant architectures, and hopefully also contribute to these research papers in the long run. All right, thank you for watching and being patient with me, because it has been a long journey, and hope to see you in real life sometime.